Hello all, welcome back to my channel. I am ready with another video, and this video is part of the series where we are making videos on uh, solution that helps us with the challenges that Spark faces, namely skew, shuffles, spill, so storage and serialization. And in my previous video, I discussed about few issues with shuffle, how and a few other options which are there with the Spark Shuffle service. Now we will see in detail how Apache Celeborn, which is an external shuffle service, helps us in reducing this shuffle. So just a quick recap on what is a shuffle. So shuffle is a process in Spark where data is redistributed across partitions, and it happens when transformation requires data to be arranged or ordered in a specific manner by key generally. So for example, group by or joins that might cause a shuffle. Uh, so these transformations which require this key, their ordering, the data ordering to be based on certain key is called a wide transformation. The example of these are group by, distinct, order by, and join. So these are certain wide transformation that cause shuffle, and this is a shuffle is actually a big challenge in Spark because that slows down the process or the job very in a very what you call uh, drastic fashion. And in if we look open the Spark web UI, we will see something like this. This stage, these are stage boundaries. So anything, any data going from one particular stage to another stage is a shuffle. So and if it is notated by exchange as well. So this is from the write side exchange. This is from the read side exchange. So this whole data is first sent to from this particular sum executor to this executor, then certain other processes are done, and then it again is exchanged. So this is exchange, and this happens over the network. So it is slightly, and it introduces the cost of serialization and deserialization as well. So the issues with shuffle is that increased network IO and resource intensive. It requires high memory and disk usage because we have to deserialize and serialize the data and also then transmit it over the wire. Hence, these are expensive operations. As we discussed in the previous blog or the video that we have created, Spark handles this. So Spark has a concept of enabling an external server service, which is based on LinkedIn's Magnet. So this service, what it does, it will run a particular run an auxiliary service on each of the worker nodes, and whenever a executor needs to do an exchange of data, it will not do exchange of data directly to the other executor. Each executor will write the shuffle data to its local or its own nodes auxiliary service called shuffle service, and then when whoever needs that the shuffle data, they will make a call to the shuffle service and get the data which is running on the node of that particular exchange service. Oh, sorry, shuffle service. There are certain challenges. The shuffle service is launched on every node, so the node goes down, all shuffle data is lost. It is not for Kubernetes workload, and no duplication of high data is not duplicated. Hence, only the data is available on a node, and if that node goes down, the data is lost. So to overcome these challenges, Spark's native ESS, there were different projects which implemented external support services like Uber's GS, Facebook's Riffle, Alibaba's RSS, which is now changed to Celeborn, and Tencent's Unifil. In this blog, we will see how Celeborn works. Celeborn is an external support service that we already have fixed it. So in without Celeborn, how what we'll say the reducer will or the cluster shuffle process will look like is this. So let's say we have this is let's say this is an executor one or mapper one. So this is map side and this is reducer side. So let's say if mapper one has access to five partitions, 50, 1, 2, 3, 4, or we can say executor one has access to these partitions, executor two also has access to these partitions, and three also. And let's say we are running some group by operation, or let's say we are running. So this reducer, let's say, is needing all things related to partition zero. This one This reducer 2 needs for partition 1, this one needs everything from partition 3. But because partition 0 is present with mapper 1, mapper 2, and mapper 3, so this reducer creates three connections, one for partition 1 at with mapper 1, one for partition 0 with mapper 2, one with partition 0 with mapper 3. Similarly, this reducer 2 does need everything from partition 1 from all the places, so it will create a connection with mapper 1 with partition for partition 1, create another connection with mapper 2 for partition 1 hold by this, and then here reducer 3 again will does the same thing and create connection. So if you see, the number of connections are getting higher. So if it was three keys, so if this based on the keys, if we have three keys and three reducer, we have 3 cross 3, that is 9 connections that is getting created. But now the same thing, how it changes with Celeborn is Celeborn will have the shuffle data and it will split the data based on the partitions. So now if you see, mapper 1 will write its shuffle data for partition 1 to this Celeborn service. Mapper 2 will also write to this. 3 will also write to this. So how many connections we have from this side? Let's say here we have 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 12. So in this case, we have 1, 2, 3, 1, 2, 3, 1, 2, 3, 9. So 9 connections from the map side, which we can't do because this data is distributed. They will have to write. But see the change with the reducer. So reducer 1, if it wants data from partition 0, now because while writing from the mapper side itself, the data is only written to Celeborn's central service, Celeborn Sultan service, which holds the data for partition 0. And then, so all these mappers wrote their partitions data to this particular partition called partition 0 in Celeborn. And when the reducer needs it, it simply says, boss, I am responsible for the keys which are in partition 0. So give me all the data which is there. And then Celeborn provides that. So only one connection. For reducer 2, partition 1, only one connection. Reducer 3, partition 3, only one connection. So see, in total, we only have 3. Here we had 9. So this is the benefit. This is the benefit that, and also because data is from all the locations, data is being sent to here, and Celeborn can do the compression. Celeborn can do the uh, chunking, merging of the file, smaller files into a bigger file, so that the reducer only has to read one file. So network I/O, the file opening overheads can also be reduced further. So this is how Celeborn helps. Uh, to achieve a shuffle in a distributed system. So what it basically does, it will have a process like this where so we will create a separate external Celeborn cluster that will have Celeborn master and Celeborn worker, and the Celeborn worker will be responsible to groups, combine and merge data from different executors. How it works is, let's say this part of the this half from here, this imaginary line, everything right to this is Celeborn cluster, and here it is everything about the driver of Spark. So what will happen first is, so it starts with here. Celeborn, when we install, the Celeborn workers register themselves to the Celeborn master. So this workers will get registered to the Celeborn master. Heartbeat from the application will, so this is a driver we will launch. This is Spark driver, by the way. So this will launch a lifecycle manager for the shuffle data, and then executors will register their shuffles with this lifecycle manager, which is driver, and then it will say that, okay, go ahead and talk to this cluster manager. So uh, executors will write the data, which is 555. So this is the fifth step where they are pushing the data to the Celeborn workers, which will store the partition data for this particular job, and Celeborn will replicate. So this, see here, we don't have one single point of failure. If this worker goes down, we can still use this worker as an primary and make that responsible for certain partitions. And this is, the cluster will still go on. No recalculation will happen. So this is how Celeborn clusters look like. It has three components: master, which is responsible for all the resource allocation and state management. It uses Raft for state syncing. Workers, these are the purposes. These are the processes which store the shuffle data. They also serve the data. This shuffle data to the executors. Also, it merges the data uh, before it sends to the reducer. Clients are nothing but that caches and pushes shuffle data. It maintains the metadata of each shuffle and runs within Spark driver. So Spark driver becomes the client for this particular cluster. Process flow, as I mentioned, it starts with mapper. So mapper registers the shuffle to the lifecycle manager, which is running in the driver. Then this lifecycle manager will request slots. So this lifecycle manager is the client. So this will request a slot from the Celeborn master. The Celeborn master will return with a slot. So, and slot will be nothing but a pointer to the worker. So this is the worker, Celeborn worker. So step three, it will reserve the slots. So lifecycle manager will reserve the slots on different workers which are there. So it can, let's say, it mean maybe the primary is worker two for partition zero, and let's say for partition one we have. So it should ideally it should be different. Like here it says that partition one is one and two both. Sorry, here if you see the partition zeros leader is this worker, so it will connect there, and partition one's leader is this worker, Celeborn 2, Celeborn worker 2, so it will be leader here, the replica will be there, and same way replica is in here. So this reserved slot, so slots are reserved, so it will say that okay, whenever you need to push data for partition 0, talk to worker 1, and if you need anything for partition 1, talk to worker 2. Once this is there, the lifecycle manager will get the partition locations from the mapper, which is nothing but an executor running somewhere, and then executor will push the data. It will provide the partition locations to this executor that okay, if you want to push data for this partition, send it to Celeborn worker 1 or Celeborn worker 2, depending upon where you want to do. So it will send the data. So let's say step number 5, it pushes the data to the Celeborn worker. What it will happen that let's say it send it to data for partition 0, so it will replicate asynchronously to other worker, which is Celeborn worker 2, and in case this worker goes down, the data will be served from this worker. So that way it keeps on replication, and we can control how many replicas we want. We can say 2 or 3, whatever we want. Then once this data is available, let's say in Celeborn worker 1 or 1, 2. This can also be flushed to a remote file system or a centralized file system. Or in let's say if it is not, it will create and merge the smaller files into a bigger files at the worker's storage location itself. And now when the let's say so 7 8, where is 8 8 8 8? So yes, mapper ends, so it will say that okay, once it has pushed the data, it has been replicated and everything is done, it will say my job is done, so executor can be removed. If wanted, then lifecycle manager will do a commit and find out where all the workers data is written, which is let's say uh, written it at let's say any place, and then let's say it receives a request from other executor, which is the second stage executor, that okay, I want data for partition let's say 0. Okay, so that is the request. So lifecycle manager first it will see let's say reducer, which is here, it asks that okay, I want data for partition 1. So it will send a request to the lifecycle manager. Lifecycle manager, because it has already done the commit, it knows that okay, which location, which particular location this partition 1 file is there. So it will say go and check files from executor, get the files from Celeborn worker 2, and that's where this reducer will talk to Celeborn worker 2 and get the data for partition 1, and for partition 0 it will get data from worker 1, and that way it will start the fetch the chunks and then process it. So this is the flow of a Celeborn process, and in a high level this is documented, and again in here I will not go through this. If you are interested or if you want to see, you can either pause this video and read this, or you can read the blog itself. So how it solves the problem? So it reduces the network connections from m cross n to only n, where n is the number of workers. It merges the files for the same partition. So instead of having many small files, it will have bigger files, which can do, and the files are written in a columnar fashion rather than in the a row basis, which earlier was the case. So the benefit of this columnar layout, right, is that if we want only certain columns, we can just get that column only. We don't have to get other columns. Also, we can have encodings there. We can do compression, encoding, because all the data is written of the same type. It will be an efficient algorithm in there as well. Deployment. Celeborn can be deployed both with Yarn and with Kubernetes. So let's see how it works with those. So at the driver, we get the lifecycle manager, and executors, we get the shuffle client, and we have this is different Kubernetes installation. So for example, let's say if we have this whole thing as an Kubernetes cluster, so Spark driver is running in isolated environments. This Celeborn cluster runs in an isolated environment, and they talk to each other via the services which is created for these master processes. Driver will have the Celeborn Spark client, and then we can talk to the cluster. And so we can create multiple, sorry, to create the cluster like this here, see this one. So we need master processes and worker processes. So if we are using uh, Kubernetes to deploy this, we can make the Celeborn jar with, sorry, Celeborn with Spark, whatever Spark version we are interested in, we can build that image with this, and then we will launch and service. We will create stateful sets for master and worker, and these stateful sets will elect a leader out of them using draft consensus, and then workers will have the data which is needed for the which will be sent by executors and which will be later requested by other executors. We need to copy the jar. So whatever jar that is there for Celeborn, if we are building the image, that will already be present. If not, then we have to supply that as an argument in the class path. Uh, so these are some certain configurations. Don't read this. This is for before 0.3 Celeborn version. This is one with the later ones. I think now 0.5 or 1 series is there out there as well. So Spark Celeborn.client.push.replicate enabled false. Fallback is to, sorry, available type is HDFS. Storage directory, then RPC timeout, Kerberos principle, and key tab. So this is in this Celeborn is integrated with Kerberos. So we can use our TCTs or tokens to key tabs to access this and control the access in that phase as well. We can also pass the jar via Spark submit jar, but with that we will have to add this extra, means use the class path first approach. Otherwise, don't use the class path first approach. Otherwise, it will fail. The reason is that it requires those applications to be present before even launching the process. So hence we have to supply this jar and set this user user class path first. We have to set to false, and then once we have done this, we will. I mean, I created this cluster and Spark, and then this tested out. So how it works performance wise. Uh, so this is Q14, Q12. So this is what you called is TPC-DS benchmark that is generally available at Spark. So all whenever a Spark releases a new version, it does a TPC-DS benchmark to see how one version is better or performing better or not performing better at certain cases. So I use the same TPCDS data set to test out the Celeborn's performance. So with Celeborn, if you see these questions are there like question 50, 23, 20 AB. These are questions, sequels that run. So question 14B didn't have much of a difference. Question 12, see the Celeborn was taking higher time, but in general, everywhere else you will see it has Celeborn taking lower time here, lower time here, here. So in general, overall, it does improve because see in these cases why it is more similar or higher time is because this doesn't have that much of shuffle. So because there was no shuffle, there was an overhead. like that. So this is something which is very much interesting to see that with TPCDS 1 terabyte size, we have seen the improvement of around 30% in job runtime. So 1 terabyte is very small when it comes to companies like big companies like Visa or the companies which are processing too much of data. They will have Spark jobs which have 50 terabytes, 60 terabytes of data being processed, and if we are able to reduce the job their runtime by, let's say, 20 30%, it's a very huge saving, because that time can be used to run some other job, or we can make the cluster available for other tenants as well without adding extra capacity. So this is how Celeborn helps us in reducing the shuffle, because it reduces the number of times the data has to go from one particular system to another system. And so yeah, this is there are some what you call pointers to note. One is fallback. So if Celeborn faces issues like there are no slots available, so it will not use this, and it will fall back to the native shuffle, Spark shuffle. And we will have certain requirement with Celeborn that we need to run this as a separate service. So in Visa, it is deployed on 3 master and 5 workers with 32 GB memory and 2 terabyte of disk on each of the workers, and then this is used for larger jobs which are running. And future we are, the Celeborn community is excited that they will be adding support for spill as well. So as of now, it is only for shuffle, where it is managing it centrally. It will be extended to spill. It will be also handling, adding support for columnar shuffle and layer storage. So layer storage means that instead of using the SSDs that are there for that we have, as I mentioned, 2 terabyte of disk, it also will have let's say if we are running on Kubernetes with local disk attached. So first it will write to the local disk. If that disk is full, then it will offload it to remote storage services, like it can be SDFS, it can be object storage as well. So that support in future will also come. So once that comes, then we can be pretty much safe that we will not have any issues related to shuffle. I mean, most of the issues will be solved with shuffle, and then we will see job run times getting faster and faster with shuffle. One thing is to note that if our system doesn't have that many shuffle, or shuffles are too sparse, adding Celeborn into picture will slow down the job. So just do an analysis. Generally, what we have seen is anything above what you call anything above uh, 500 GB of shuffle should go through the external shuffle service. So anything less than that can still rely on Spark's internal inbuilt shuffle service and will still work on fine. So yeah, this was it for the shuffle service. We will see you in another video, which we will discuss about maybe about Spark accelerators or native engines. So stay tuned and spread the word. If you like this video, do subscribe and share it with your folks who will like to see more such content. Have a nice day.